Hello everyone, my name is Meng Lian from Technical University of Munich. It is my honor to attend the ISPD virtual conference. As you can see on the screen, our topic today is FXT router, efficient high-performance PCB routing with crosstalk reduction using spiral delay lines. In high-performance printed circuit boards, added serpentina delay lines is the most prevalent delay matching technique to balance the delays of time-critical signals. Serpentina topology, however, can induce simultaneously accumulation of the crosstalk noise, resulting in erroneous logic gate triggering and speed-up effects. In the following, I will introduce our routing method, which adopts spiral delay lines to address the delay matching issue while effectively reducing crosstalk noise and achieving high-density transmission lines. As the propagation time of a signal is directly proportional to the wire length, adding delay lines to the shorter wire is the typical method to introduce a propagation delay between circuit board elements to balance the delays of time-critical signals. The serpentina delay line is commonly used for delay matching. However, in high-speed digital circuit applications, serpentina delay lines introduce, besides the desired delay, spurious dispersion that makes the signal arrive sooner than expected. This phenomenon, known as the speed-up effect, is mainly attributable to the synchronous accumulation of the crosstalk noise between adjacent wire segments. The state-of-the-art approach for crosstalk alleviation achieves waveform integrity by enlarging wire separation. In the following, we elaborate on the propagation of the main signal and the crosstalk along the serpentina and spiral delay lines. Since the coupling between two parallel wire segments depends primarily on their separation, the crosstalk pulse induced within the mth and nth wire segments is of magnitude k, index absolute value of m minus n over 4, where kp denotes the average of the capacitive and inductive coupling coefficients separated by p wire segments. Let Td indicate the time for a signal to travel along one wire segment. Suppose that at time 0, the main signal appears at the near end of L1. Due to the electromagnetic coupling, the signal simultaneously induces crosstalk noise in all other segments. Omitting the noise propagating toward the source, we focus on the leftward propagating crosstalk at the near ends of L2, L4, L6, and L8, which are pulses with a 2 Td width and K1 over 4, K3 over 4, K5 over 4, and K7 over 4 voltage respectively. As the signal propagates along L1, the crosstalk pulses propagate from L2, L4, L6, and L8 to L3, L5, L7, and L9 respectively. At time Td, the main signal and crosstalk pulses reach the respective far ends. After that, the main signal travels along L2 and induces additional rightward propagating at the far ends of L3, L5, L7, and L9. The process of crosstalk accumulation is repeated until the main signal reaches the receiver at time 9 Td. Since the crosstalk noise is inversely proportional to the wire segment separation, the most significant crosstalk is the crosstalk between two segments in the closest neighborhood, called the adjacent crosstalk. We illustrate the corresponding time diagram of the crosstalk due to the adjacent coupling in the serpentina delay line in the figure on the left and the corresponding receiving waveform in the figure on the right. As shown in the time diagram, the main signal induces 8 adjacent crosstalk pulses before its arrival. These pulses simultaneously arrive at the receiving end at time 7 Td and are superposed as a large wave of magnitude 2 K1. This accumulation may exceed the threshold of logic switching at the receiving end before the main signal's arrival, leading to a speed-up effect on the wire. As with the serpentina delay lines, at time 0, the main signal switches at the near end of L1 and propagates from left to right. Meanwhile, The adjacent crosstalk pulse of magnitude k1/4 induced by the main signal at L1 at time 0 proceeds straight to the receiver. At time td, the main signal propagates to the far end of L8 and induces two adjacent crosstalk pulses of magnitude k1/4. The one at L9 directly appears at the receiver. We illustrate the corresponding time diagram of the crosstalk due to the adjacent coupling in the spiral delay line in the figure on the left and the corresponding receiving waveform in the figure on the right. As with serpentina design, the crosstalk noise is continuously created as the main signal propagates further toward the receiver. Still, these pulses reach the receiver at various time intervals. In other words, the crosstalk is accumulated asynchronously and spread over time ahead of the main signal. In particular, the magnitude of the crosstalk noise in the receiving waveform constantly stays at k1/2. Consequently, regardless of the number of delay line segments, the erroneous logic gate triggering does not occur as long as k1/2 is smaller than the voltage threshold at the receiving end. Our method generates one wire at a time. Each wire generation involves two phases, the along-the-edge routing and the length compensation utilizing spiral delay lines. The center of the routing area is typically densely populated with many wires, easily resulting in severe congestion. Considering this, we generate one wire at a time, starting from the edge of the routing area and maximally reserving the center for unrouted wires. We implement our routing algorithm by constructing a mixed integer linear programming model to determine the wire's main path between its two target pins alongside the free space boundary. A wire is formed by several vertical and horizontal segments. When two consecutive segments span in an orthogonal direction, a bend occurs, and the point of the bend is referred to as the bending point. Since vertical and horizontal segments form the wire, the free space boundary is a rectilinear polygon. When the wire is routed alongside the rectilinear polygon from the interior, only the corners cause the wire to bend. In other words, the point at a distance of the minimally acceptable unit length delta from the x and y coordinates of the polygon's corner is most likely to be a bending point, referred to as P convex for the convex corner and P concave for the concave corner, as shown in the figure, respectively. We define these points as the bending point candidates. Moreover, if an obstacle is at the position of concave bending point candidate P concave, we create four alternative candidates, P concave 1 to P concave 4, to guarantee that the wire will bypass the obstacles. Finally, our algorithm selects bending point candidates to serve as bending points to form the wire's main path. After determining the currently considered wire's main path, we add spiral delay lines to compensate for the required wire length. As the orientation of the spiral's terminals can be either at opposite corners or on the same edge, we define two primary spiral types, convex and concave spirals. Taking advantage of the rectangular form of the spiral's outer frame, we propose to use the spirals to fill in the nooks and crannies of the free routing area. To this end, we require that at least one of the spiral's corners overlap one of the boundary's corners, and the spiral's width and height should not exceed the length of the wire segments connected with that corner. We show the areas for spiral synthesis for convex and concave corners in the figure. Further, to improve the allocation of free routing areas, we provide a weight coefficient within the closed interval from 0 to 1 for each boundary's corner to reflect the severity of routing congestion after the spiral synthesis in that corner. The larger the weight coefficient, the higher the priority for spiral synthesis. After that, we select the areas with higher priorities to place the spiral delay lines. We implement our method for spiral synthesis by constructing a quadratic programming model for wireless compensation. In the following, we investigate the performance of the along-the-edge routing model and our length composition technique using 6 layout designs as test cases. The table demonstrates the routing efficiency of our method. In our experiments, the minimally acceptable unit length delta is set to be 1. Supposing the wire segment separation is 1 unit length, then adding 1 unit length wire segment is equivalent to occupying 1 square of area 1. Therefore, to compensate for the required wire length, denoted by L tot, the routing area should be at least L tot. In other words, without considering the feasibility of the routing result, the maximum routing area reduction is the difference between the total routing area and L tot. The percentage ratio of this difference in the total routing area, defined as the free space ratio, evaluates the utilization of the routing area. Specifically, a smaller free space ratio indicates less wasted area. As shown in the table, our method can effectively reduce the free space ratio to less than 18% in all cases. On average, the required routing area decreases by 31% compared to the original routing result, leading to lower manufacturing costs. Further, we show the experimental results for case 6. Figure A shows the routing results proposed by Yan applying serpentina delay lines for delay matching. Figure B shows the routing results proposed by Zeng with wider Minder segments. Specifically, the separation between parallel wire segments is 1.6 times larger. We can see that the results in Figure B also have a more uniform wire distribution than in Figure A. Our result, employing spiral delay lines for delay matching, is illustrated in Figure C. The figure shows that the nooks and crannies of the routing area are filled by adding spirals, and a large surplus of free space remains in the central area. To quantify the reduction in routing area requirements using our method, we decrease the height and width of the original routing area and reroute within the minimized routing area. The final routing result is illustrated in Figure D. Compared to the original design in Figure A, we reduce the required routing area by 10.99%. The height of the routing area is significantly reduced, and there is almost no wasted routing space. To compare the accumulated crosstalk of the routing results with different segment separations, we express the magnitude of the accumulated adjacent crosstalk for an arbitrary delay pattern in Kd, where Kd is the coupling coefficient for the near-end crosstalk induced within 2 parallel wire segments separated by D. For case 6, we calculated the crosstalk magnitude of each wire for each routing result. The calculation results are presented in the table, where Vmax and Vaverage denote the maximum and average crosstalk magnitude among 36 wires, respectively. Observing the magnitudes of the accumulated crosstalk for the results in 1 and 2 indicates that by enlarging the separation between parallel wire segments, the accumulated crosstalk is effectively alleviated using the method in 2. As for the proposed method, our method significantly decreases the maximum and average magnitudes of the crosstalk noise while routing in the original routing area. Compared to the method in 1 and 2, the maximum and average levels of crosstalk in our routing result are at least 39% lower. When the total routing areas are reduced, the shrunk space increases the number of spirals and, consequently, the crosstalk magnitude. Still, our method can significantly reduce the disturbance caused by crosstalk noise in designs with a small free space ratio. Further, in the figure, we present the crosstalk magnitude accumulated within each wire for case 6. The figure on the left shows that the crosstalk noise in our routing results is significantly lower than that of other methods for almost every wire. Besides, we illustrated the crosstalk magnitude of each wire in our results, routing in the original and minimized the routing errors in the figure on the right. The line chart demonstrates that the crosstalk noise level is not notably impacted while the routing error is decreased. In conclusion, our method is reliable in alleviating the accumulated crosstalk noise. That was my presentation, and thank you for your attention.